Okay. So I remember last week we talked about these steam tables and some refrigerant tables also, and we showed you how to use these tables and how to find the values from these tables. Sometimes for some gases, we can't find the values in tables, or let's say we don't have the table available with us. So what we can do is actually we can, if the gas is ideal gas, we can always use a formula to find out the values for, let's say, pressure, temperature, volume. So this formula, we call it gas constant or ideal gas equation. So let me take you to that. Yeah. So okay, so the ideal gas equation of state, or they call it ideal gas relation. As we said, like property tables, they are quite accurate to get the information about the properties of any pure substance. But sometimes, as I said, for some reason, we can't find these tables, or we can't find the value from the tables. So if the gas is ideal gas, then we can use this equation. We call it ideal gas equation. If you look to the equation, the first one here, we call this ideal gas equation. And it's simply, it's the pressure multiplied by volume equals the mass multiplied by R, which is the gas constant, multiplied by T. So R, which is the gas constant, this value is constant for each type of gases. So for example, for air, it has different value from helium, or from different value from hydrogen. So each gas has its own R value. So if you know the R value, which is constant, most likely we can get it from tables. Then if you have, let's say, P is unknown, you need to find P. So you can say P from this equation is equal to the M R T temperature divided by the volume. So you can find the pressure of the gas. Vice versa, if you want to find the volume, you divide by pressure. So it's quite straightforward. All you need to know is you need to find the value of R from tables. So in most questions, they provide R in the question. But if you don't have the R, you can always go to tables. So you can find for each gas. I will show you these tables very soon. And in the table, you can find out the R value for each gas, or ideal gas. And this is like table A1, as you can see. So for each, for example, for air, we have the gas constant R. So for air is 0.287. This is the R value. And for, let's say, any other gas, for example, for oxygen, we can find the R value for this. And you can see the oxygen is quite close to the air, because most of the air is oxygen. So they are very close to each other. But if you choose any other any other gas. For example, the argon, it has, or ammonia, it has different, completely different from the air. So this is the way that you can find out R value for each gas. And then once you know the R value, as I said, you can substitute in the equation, in the ideal gas equation, which is the PV equals to MRT. So the R here is what I get from the table here. Okay. All right. And for example, let's practice this. Let's see what's the difference between the tables and the ideal gas equation. I'm using now steam table, superheated steam table. Although the superheated steam is not 100% ideal gas because doesn't have the condition of the ideal gas, but still we can use the equation, what we said, equation PV is equal to MRT. All right. For example, this equation, this for example, in this example, use the ideal gas equation to find the pressure of the refrigerant. So this is refrigerant 134A. So the table A13 represents the superheated refrigerant 134A. And I want to compare the value in the table with the value from the equation. So in this equation, in this example, we need to use the ideal gas equation to find the pressure of refrigerant. So what we need to do here, we have given all the information. We have given the temperature, we have given the specific volume, we have given also the R value. So we can write down this equation. If we have it per kilogram, we can do it in terms of specific volume. So we can say P, we divide by M. It's going to be P specific volume equals to RT. Right. So now what's the pressure? The pressure will be P equal to RT divided by specific volume. Now, R, what's R?
0.0814.
Yeah, correct. So O 0.0814 multiplied by
60.
Okay, so when you
need to convert it to Kelvin, right?
Yeah, we have to add 273 to the Celsius to make it Kelvin. So make sure that when you use the ideal gas equation, you always, when you find T capital here, T capital most likely represents Kelvin.
Kelvin, okay.
Okay, so we're gonna do it now in Kelvin.
333.
Yep. So we're gonna say P will equal to the 0 said 0.0814 multiplied by 60 plus 273.
333. 333.
33?
Yep.
Divided by specific volume, which is 0.0. Yeah.
0.023.
Yes. Can you please find out the result here? Someone with calculator can help me and find the result. So
1178.
1100.
78.
78. This is the pressure in Pascal, correct? But just notice here, what's our value in joule or kilojoule?
It's kilojoule.
Kilojoule.
So it
Should be kilopascal.
Kilopascal, yeah.
Yeah. Okay, so be careful. When you use kilojoule, it will be the answer will be in kilopascal. It's if it was in joule, then the pressure will be in Pascal. Okay, so now the result I have R in kilojoule, I should have kilopascal. Okay, now let's check this. If I have the pressure 1178, so it means if I go to this table give me the pressures in megapascal. So I need to divide the result by 1,000. So this will be 1.1 megapascal, right? So if I compare this now with what I have in the table, if I take the temperature in 60 Celsius given in the example. So I go and also check the specific volume 0.023, correct? So where is the specific volume? The column, the first column, right? This is the first column, specific volume. If I go along this and check where is the value of 0.023, it will be somewhere.
It's between the first and the second one, somewhere between.
Yeah, correct. So this is where I find the 0.023, the specific volume. And what's the pressure for this?
Pressure is 1178.
No, yeah, but no, in the table. For this value in the table.
Oh, in the table is 1 megapascal.
Megapascal, yeah. So 1 megapascal compared with this one here, it's close. So this one 1.1, this one 1, but it's not very accurate.
Yes,
okay. But this is like just to give an idea. Sorry?
The temperature is the same, sir.
Yeah, exactly. Not 100% exactly same because no, this temperature is 60, correct? So you can,
but
if you go
here
to the
it's 39.37.
The specific volume. Yeah. No. This 39. This is saturation temperature. This is not the. Yeah. You look to the first column. The first column shows this one shows the temperature. Okay.
Oh,
so in this column, you check your temperature, which is you go to the 60 here, and at 60, along this, you find that the closest pressure to the specific volume that we have, which is 0.023, comes at this, correct? And this falls in the table of pressure 1 megapascal. So this is just give you an idea. We can do the same thing, but different way. If we have the pressure and we need to find the specific volume, same thing. We can use the ideal gas equation to find the specific volume. This is just to give you an idea difference between the ideal gas equation and the table. You don't have to worry too much about this. You don't have to compare your values with the table, but I just want to show you that what's the difference between the two values. The table is more accurate, but if you don't have tables, then you can always refer to the ideal gas equation. Am I clear?
Yeah, great. Doctor, I have a question about the tables.
Yeah.
I need to use table 1 or table 13 for the ideal gas?
Table 1, let's see which one is a table 1. 1 second, let me check. You mean this one?
Yeah.
But this one, yeah, I mean, this is the table where you can use it to find R value, correct? So you go to this table, you find R value. What was the R value we had for refrigerant, which is this one here? Refrigerant 134A. It was this one, 0.08, correct?
Yep. Yeah.
If you go to the question, this is what we actually, but they gave it to you rather than you go to the table, find the R value. It was given in the in the example. So as you can see here, can you see this one? We already given this, but if you don't have it, if the question doesn't give you the R value, you can go to this table and find out the value based on the name of the gas. So you find out what gas you are working with, find R value from the table, and then go back to this equation, substitute in the PV-RT equation.
Because I'm a bit confused about the tables. So what do you need?
Yeah, no, but this is why. Most of the time, we give you the R value. This value is given in the example, but just in case if you don't have it, you can go to table 1 and find out R from that table. Okay? Okay. All right, so this is actually in brief about the ideal gas equation. There are other way to find out the property of gases, ideal gases. I will not go into details. There is, let's say, what they call it, compressibility factor. And this is based on what we call reduced temperature and reduced pressure. There is a special chart here, and this chart is quite complicated. But again, this is for future studies. If you want to, let's say, if you have a research or a project you want to work on, and you want to find the value of the, 1 second, sorry. Yeah, just can you hold on a second, guys? I will come back because my battery will.
Okay, doctor, take your time.
Good, sir.
Okay. So this is another way that to find out the property of ideal gas. We call it compressibility factor. So you are not required to go into details, but this is just for future studies to show you how to find the property of ideal gases. So the major one here is what I want you to do, or what I want you to use, is the ideal gas equation. Again, it's P V equal MRT in terms of the mass, or per kilogram, it's P specific volume equal to RT. Please remember this equation. And as we said before, T should be in Kelvin. always. If you put it Celsius, then this will give you a wrong answer. Okay, and make sure that if it's R in joule, then P gonna be in Pascal. And if it's in kilojoule, then this one should be in kilo Pascal. All right? Am I clear?
Yes, doctor.
All right. So by this, we finished the last week lecture. Take you to the new topic or new lecture 4. In this lecture, we will have some information about energy analysis of a closed system. Remember, before we mentioned when we talk about the system, we said we have two systems in our design or in our study. We have a closed system where the flow of the fluid enclosed or doesn't cross the boundary of the system. So the mass will not cross the boundary of the system. And we have open system when we have flow in and flow out. So in this lecture, we're going to talk about the closed system. We'll have some information about how to find out the work of or moving boundary work, and also how to plot the work on pressure volume diagram. We'll also introduce you to a new process, real life process, which is, we call it polytropic process. Remember before we talked about the process in previous classes, we said that we have isothermal process and constant pressure process and constant volume process. The fourth type is the polytropic process, which is the more real, relate to the real life systems. And also we'll talk about how to make energy balance, as well as how to use the specific heat to find out enthalpy and internal energy of the system. So we'll take it one by one. But the first thing we need to know, the moving boundary work. So what do we mean by moving boundary work? If you look to this figure, which is the traditional piston and cylinder system. In this system, we have air enclosed or captured inside the cylinder. And for any reason, let's say if I provide heat to this air, then what's going to happen, the air will expand because of the added heat. And the expansion of the air will cause the piston at the top will push the system upward, and piston start to move. So we call this the process involved work or moving boundary work. And how to find the work from this? By applying the normal equation of the work. You know that the equation of the work is the force multiplied by the distance, the travel distance. And if we know that the travel distance is ds, this is how much distance the piston moved from initial position to the second position. So from position number 1 to position number 2, the distance was ds. So I can say, if I have the force, so I can say F multiplied by the distance ds. And ds basically, or F first, F, the force is the pressure multiplied by the exerted area. So if you know that the piston has a circular shape. So this piston is a circular shape like this. And if I know the area of this circle, the area of the piston, then I can multiply A by the pressure to get F. So I replace F with this value, PA. I replace F with PA, and then I can say PA ds. This is the work done. And then I can put these two together. The A multiplied by ds represents volume. So remember, if I want to find the volume of this part, it's simply the area of the circle multiplied by ds. So it's the area multiplied by ds. This will give me the volume, dV, change in volume of the gas. So I can use this in the equation of the work, and then to find the total work, I just simply integrate between two points, between 1 and 2. So integration between 1 and 2 will give me the work done or moving boundary work. Okay, that's simple. Any question?
Thank you.
So now if I want to represent this on a pressure volume diagram, look at this diagram here. The y-axis represents the pressure, the x-axis represents the volume or specific volume. And now if I'm moving the piston this way, if the piston is moving to the right side, then I will start from point 1 at this position. Okay, this is my initial point, right? This is my initial point. So I'm moving the piston to the right side. So it's what we call it expansion. Why expansion? Because we are increasing the volume of the air. Starting from point 1, it was a small volume, as you can see, V1. And then when I move to the right side, up to say point 2, V2, then this is the maximum I can go in the cylinder. So the volume, the change in volume will be V2 minus V1, correct? And now to find out the work done of this boundary, the work done on the piston, I simply apply the equation mentioned before, equation which is the W, the work done is integration of P dV. Okay. We are assuming all the time here that we have the Gaussian equilibrium expansion. Remember before we mentioned, I think the two lectures, we talked about the Gaussian process or Gaussian equilibrium process. We said that this process is an ideal process. We are moving the piston in a very slow motion where we keep the system under equilibrium. There is no change, sudden change in temperature or pressure while we are moving the piston. So in this kind of expansion, Gaussian equilibrium expansion, applying the general equation for the work, which is the integration of the PDV, we can find the work of the boundary. Now, if I have a cycle, remember, if I expand, let me take it this way. Okay, if for example, I take it this way. Again, this is the pressure volume diagram. So this is the pressure, this is volume. And this is pressure and volume. Now, if I have, for example, expansion in this way, we said that the area under the curve represents the work done, because the integration between 1 and 2. Okay, if I want to do a cycle, I have expansion and then compression, which we call it a cycle, because in most of in all type of systems, we don't move one process. We keep the system operating. For example, for let's say the car engine, the operation of the engine is continuous. You don't take one process and that's it, because you need to keep the engine operating all the time. So we have to expansion and compression all the time. So the network is the work enclosed by these two processes. This is the amount of work I can get from the system, because one of it is for the compression, I need to consume work. In another way, I produce work. So the net one will be the difference between the produced work and the consumed work, which is the one between two processes here. We will come to this later on, but just to show you what we mean by network in a cycle, okay? The work done depends on, again, on the process that we have. So remember, we mentioned before that we have, let's say, isothermal process where we have constant temperature process. So if you want to find the work during this process, again, we apply the general equation of the work, which is the W integration between 1 and 2 PdV. And then we have the ideal gas equation mentioned before, which is PV-MRT. Now, if it's constant temperature, I can replace the pressure here with this equation. So I can say P is equal to MRT divided by V. And I replace this equation, put this MRT divided by V, replace the pressure by this value. And then when I simplify the equation, I can find out the work done. Because temperature is constant, I can take the temperature and R and M outside the integration, and I end up with dV by dt, integration dV by dt, which is MRT ln V2 by V1. So for isothermal process, if you know the temperature, you know, of course, the R from tables, the mass, if mass is given, then you only need to do is you find ln V2 by V1. If you know the specific volume at the beginning, specific volume at the end, you can find out the work of the system or work done by the boundary. Okay. I know that it seems a bit complicated, but we will have a question very soon and we'll clarify everything. So this is the final equation for isothermal process. This is the way you find out the work for isothermal process. So either you say MRT ln V2 by V1, or you say, rather than saying MRT, say P1 V1, because MRT is equal to PV. So you can say P1 V1 ln V2 by V1. Okay. Okay, is it clear, guys? Any question?
No, all good.
All right. Okay, so let's practice this, because this will give you a clear idea about what are we talking about. Okay, in this example, again, we have a piston and a cylinder. Remember, we mentioned that in this lecture, we are talking about a closed system. So in a closed system, there is no flow across the boundary. So which means that, let's say the air in the cylinder doesn't leave the cylinder. We're always talking about a closed system here for this lecture. So now we have a piston and a cylinder, this is the closed system. A piston and cylinder device initially contains 0.4 cubic meter. So we know the volume of the air. We can say this is initial V1. So we know that V1 is 0.4. What's P1?
It's 100 kPa.
100 kPa, correct. And Bakhtiar, Elias.
Yes, sir.
What's the T1 here, temperature, initial temperature?
80 degrees Celsius.
80 degrees, correct. And so in this process, as you can see, the temperature is constant. You can, if you look to the graph here, the pressure volume diagram, the temperature T1 is equal to T2 and equal to 80 Celsius. So we have what we call this process constant temperature process.
Isothermal.
Exactly, isothermal process, yeah, or constant temperature process, correct. So we have the initial condition, V1, P1, T1. Now they said the air is compressed to 0.1 cubic meter. When we say compressed, is the volume, does the volume increase or decrease?
Decrease.
So it's a volume decrease.
Decrease, because when we say compress, we are talking about reducing the volume. If it's expand, then we are increasing the volume. Okay, so we need to know the work done during this process. So can you please, everyone, work out this? Try to, let me give you a clue for this. I need to, you need to use the equation, the thermal process work from previous, this is the equation we used, or this one. So I need to use one of these two. Can you write down these two equations, please? So work done for isothermal process. Write down on a paper, separate paper, and I will ask you after that, what's the value of work done? It's quite important to know how to calculate these using the calculator, because sometimes you forget how to find out ln, let's say, how to find ln of a value. So it's good to practice this yourself. Just do not only rely on reading the question. Try to solve it by yourself, and you'll be be more professional in using the calculator. And because during the exam, time is important. And if you are, let's say, very slow in using the calculator, then you will consume more time in solving each question. So please try to practice this from now. Did you everyone wrote down the two equations? Okay, so we go back to the question. Now, can you please apply these equations, one of them, on this condition? We have temperature already given. You know the volume 1 and volume 2 already given. You can find out the work done. It's quite simple, just straightforward. You can say W is equal to P1 V1.
1000 multiplied by volume, which is
Yeah.
0.4.
Yeah. Sorry. Can you say it, please, again?
100 multiply.
Remember, the temperature must be in
Kelvin?
Kelvin, yeah. In any equation in thermodynamics, use Kelvin. Don't use Celsius because it gives you different values. So if you are using PV-MRT, then T should be in Kelvin. So you have to add 273 to the 80. Okay.
So are we gonna use the first equation or the second equation?
Oh, it doesn't matter. Should any one of them
sir,
will give you.
I think the second one. So we're
the
gonna
second one is much easier than the first one, I guess.
Yeah, that's right. That's right. So whatever
Because the question is
available
separate.
data you have, yeah, use it. So Melhem, sorry, Meleh Tariq.
Hello?
Meleh Tariq,
Yes, sir.
have you done anything? Did you try to find out the work?
Yes, so P1 V1,
Yeah.
V2.
So you're gonna use
Is,
P1 V1.
Yeah,
So
I
you're gonna
found
use
out
this one,
that
right?
the second one.
Yes,
You're gonna
yes.
use this one.
Yes,
Yeah.
I'll use that
Okay. So P1 V1 ln V2 by V1. Yep.
one. Yes, which is end up with 55.45.
5.45 kilojoule.
Yes, that's what I found.
Okay. So we'll substitute this here. Let's find out 55.45 kilojoule, right? This is what you got?
Yeah, correct. Doctor.
Yeah. So
Yes,
I
sir.
think
Okay.
the negative is due to the compressions.
Yeah, correct.
Is it supposed
That's
to be
what I'm trying
negative?
to correct. Very good. Who answered this? So
Sir, me, Imran.
yes. Sorry, who was saying negative because compression?
Sir, Imran.
Yeah,
Me.
Abdulaziz.
Imran. Yeah, Imran. Yeah, sorry, Imran. Yeah. So that's a good point, Imran. Everyone should notice this place. If you have minus here, don't feel it's wrong. Correct? Because in compression, remember before we said that if you have a system, the sign convention of the system, if you have work produced from the system, we give it positive sign. If the work going into the system, which is our case now, we have compression, we are adding work to the system, we should have negative value. All right. While if we have Q is opposite to the work. If you have Q leaving the system, then it should be negative. And if we have Q added to the system, then this should be in positive. It's opposite the work. Okay, so the convention of the heat opposite the convention sign of the work. All right. So in this case here we have compression, because in the example they said it's compression, and this means that we have work added to the piston. We are compressing the piston, mean we are adding work to the system. So that's why we have negative sign here. Okay. All right. So this is just give an example how to use the ideal gas equation as well as the work during a certain process. Okay. So we said before that we can take you also to show you what's the actual process, what the real life process which is what we call it polytropic process. So during an actual expansion or compression process of gases, we should follow this equation. Remember before we said we are using the PV equal MRT. Now the constant, the PV is raised to the power n, okay? And n is the process or the constant of the polytropic process. So rather than we have only PV in the ideal process, we say PV equal MRT. Now we have PV to power n. So that's for the actual process, and n must be provided in the example or the question. We need to know n because this is the n represents the type of expansion or compression of actual process. And so that to find the work done by polytropic process or the actual process, you need to follow this. Again, we're going to apply the integration of PDV, the same principle we followed before, but in this case, we're going to, rather than using V by itself, it's V to power n. Okay, so remember before we said dV by V, now dV by V to power n. Okay, and if I simplify this, I can get the work for a polytropic process represented by this equation. So this is the work for a polytropic process. As you can see, it's again requires the pressure volume of initial and final divided by the n. The n, we said the n is the power of the polytropic process, and n should be shouldn't equal 1. If it's 1, then it's ideal. It's ideal process. But for an actual process, n should be like greater than 1 or less than 1, depends on the process. So this is like in brief how to find out a work or the work in a polytropic process. Again, all these equations will be provided in a formula sheet. Let's say, for example, in final exam, you will be provided with, or you will have a formula sheet. Or if you have an open book exam, then you can always refer to the lecture materials and find out the equation. You don't have to memorize it, but it's good to know how to use it, because otherwise, when it comes to application, it's be very hard to find out which one you're going to use, this equation or the one before that for, let's say, isothermal process. So please make sure that if it's polytropic process, use this equation. Otherwise, use the other equations for, let's say, isothermal process or constant pressure process. Okay. Right, so let's have another example here. And in this example, again, we have a piston and cylinder. A piston and cylinder device, and we know the volume of gas. So the volume of the gas is 0.05. It's already given. This is the initial volume, and we know the initial pressure. So we have P1 and V1. We have a spring on the top of the piston, and this spring always exerting pressure downward, trying to push the spring downward. So in the initial condition, the spring was at rest. There is no movement. So, but the spring has what they call it spring constant, and this spring constant depends on the type of spring. Each spring has different constant. So the reason why we have given this spring constant to find out the force of the spring. So we will show you how to find out the force from a spring. But for the time being, we know this constant, spring constant, and we said that it's touching the piston, so there is no, it's under equilibrium condition. There is no movement now. Now we start to supply heat to the cylinder. So when we supply heat, as we said before, the gas start to expand. So when the gas expands, start to push spring upward. Correct? Start to push the spring upward. So, and we have the pressure of spring downward. Okay, so when the spring expands, it has to overcome the pressure of the spring as well. So the total pressure at the end should be the pressure of the gas plus the pressure of the spring, because this is the total pressure we have. Now, what they said here, when we supply heat to the gas, the expansion will be up to a volume which is double the volume of the initial one. So if, as I said here, the volume inside the cylinder will be doubled. If you can read this, the cylinder, the volume inside the cylinder doubles. It means that if it's initial 1.05, and then what will be V2?
So it will be 0.05 into 2.
So double 0.05 will be 0.1, right?
Yes, Doctor. 0.1.
Correct?
Yep.
Because you are doubling the 0.05. Correct?
Yeah, because 2 multiply 0.05.
Yeah. So that's the V2, the final pressure. Remember in gas, in ideal gas equation, you always need initial and final condition. So you need, let's say, if you have initial pressure and final pressure, initial temperature, final temperature, initial volume, final volume. So any one of these missing, we can find it easily. So, but you need to find the other properties for initial and final properties. So in our case here, we know the initial volume, and we know the initial pressure, and we know the final volume. Okay, so the requirement here is find the final pressure inside the cylinder. So they want to find out P2. So P2 is missing here. Okay, so we don't know P2, right? So what we need to do here, again, we said that V2 is equal to 2V1, and we found that this is the value of V2. That's good. We can apply the ideal gas equation for other values. So before that, in order to find out the pressure of the spring on the piston, we need to know the what's the distance traveled.
Yeah,
or
to know the force.
How much? Yeah, how much spring was, like the length of the spring, change in length of the spring, because this represents the change in the force, or change in volume, change in pressure. So X here, which is 0.2, represents how much we move the spring upward. This is the S, X. Okay, so if we move the spring from initial position 1 to 2, then the travel distance is X. So we can find X if we divide initial volume or the change in volume divided by the area. Okay, so as we did here, we have final volume minus initial volume divided by the area of the piston. We can get X, which is 0.2, right?
Right.
And then if we know X from the spring constant, we can find the force of the spring. And you don't need to worry too much about this, because always, like, you know, for the property of any spring, if you need to find the force of that spring, all you need to do is to multiply the K, the constant of the spring, multiplied by the distance change, or the length of the change in length of the spring. And we said the length of the spring is 0.2 meter. So I can multiply the constant 150 multiplied by the 0.2 change in the length of the spring. I can get the value of the force of the spring. Okay, so the force of the spring is there. I can divide it by the area of the piston. I can find the pressure, because remember, the pressure is
Force
divided area, correct. Okay, so that's the pressure applied by the spring, 120 kilopascal. Now the final pressure, remember, the final pressure represents two pressures. The pressure of the spring, because the spring trying to push the gas downward, and also the pressure of the gas because of the heat. So if you add them together, you will get the final pressure of the inside the cylinder. Okay, so again, let me clear this. So now, as you can see here, we have the pressure of this. The pressure rises linearly from 200 to 120. So we have 200, which is the initial pressure, plus the pressure of the spring, because we are trying to push the spring upward, and spring is pushing the gas downward. Then the amount of pressure of the gas inside the cylinder must overcome this. So we have to add 120 to the initial pressure to get the final pressure of inside the cylinder. Okay, is this clear for everyone? Now we come to the work done of the piston, or work done by the gas due to expansion. So remember, we have expansion inside the cylinder. If I go back to this figure, can you see the movement is upward, which means that I'm increasing the volume of the gas. If I'm increasing the volume, we said it's expansion. And because it's expansion, then we're gonna produce work from this process, because it's expansion. So backward to what we were talking about here. If I want to find out the work done by the gas inside the cylinder, I can do it in either way. I can use the equation, the ideal gas equation, or I simply, the work done is between 1 and 2 is the area under the curve. So this is the area under the curve. So if I know the initial pressure is 200, the final pressure is 320. Okay, and I can say from this drawing, the area under the curve, which is a trapezoid area, I can find the work done by the gas on the piston. Okay, so simply you just take this, try to find out the area under the curve. You have these volumes here, it's already there. And you take the pressure, initial plus final, divide by 2 to get average pressure, and then multiply it by the change of the volume. You get the trapezoid area, which gives you the work done by the gas. Okay? Is it clear? Any question?
Sir, can we use the formula for the work done?
Yes, yeah. So yeah, you can use, okay, here, let's say an easy way of finding the work done is you just, you plot it on the PV pressure volume diagram to find the area under the curve. Also, you can use the formula work done integration of PDV, okay? And the change of volume here is from volume 1 and volume 2. So we can say W simply PDV or P delta V, correct? And P, we take it as average, P average. So P average is 320 plus 200 divided by 2 and multiply this by delta V, which is the change in pressure. So delta V, sorry, change in volume. Delta V here is equal to 0.1 minus 0.05. Okay, this will give you the same result. Okay, Imran?
Yes, sir.
It's clear?
Okay. Yeah, it's clear.
Yep, yep. Okay. The last requirement is the work done by the spring, which is, again, it's just simply, it's force multiplied by dx. We already found x from previous, we found x here. The x is 0.2 meter. So we're gonna use this x, because this is a change in the distance or change in the length of the spring. So we're gonna use this 0.2 to find out the work done. Again, the work is the F dx between 2 points. And because the change in x from x1 to x2, so initial x is 0, and then final x is 0.2. Okay, so that's, will give you the same, okay, to give the answer or the spring or the work done by the spring. Okay, it's simply just use the force of the spring to find out the work of the spring, which is 3 kilojoule. You compare this with the gas, it's the gas for 13 and this one is 3 kilojoule. Okay, so the net work will be 10, because we are trying to, the gas trying to push the spring upward, spring trying to push it downward. So the work, they are opposite to each other. And the net work will be 13 minus 3, which is 10. Okay. All right. I know it took a long time in this. I need to take you to a practice, to Kahoot practice. Just we take this final comment here or final topic, and then we'll go to Kahoot practice. So now we knew how to find out the work for a closed system. Now, if I want to apply this on an energy balance, because now if I know the work, I know the Q, I can apply energy balance for a closed system. and energy balance of a closed system, we said before this, energy balance follow this equation, the red frame one, the one shown here in red. So we said always we need to consider all type or all the work entering the system and all heat entering the system must equal the change in internal energy of the system, delta E, which represents the kinetic energy, potential energy, and U, internal energy of the system. So for any application, if we have, sometimes we have this part equal to 0, we end up with delta Q equal delta W, okay? So this is the simplest or the simple shape of the equation. Delta E system, if we said that if it's this delta E is equal to 0, then we end up with work net equal to Q net. Okay, so delta Q equal to delta W. Okay, all right. All right, so this is a question that we're going to use in Kahoot. Let me explain this question to you, and then we go to Kahoot and try to practice this. I want to see what's your knowledge so far. Do you understand what I'm talking about or not? You need more like explanation. So, but let me explain this, and then we go to Kahoot because you have already some idea about the question. So in this question, we have a piston and cylinder again, a piston and cylinder device. We have the initial condition, as you can see here, we have V1, P1, T1 all given. And then this piston at rest, as you can see, the pistons rest on two stoppers here, these two stoppers. So it doesn't go downward, it's resting on these stoppers. And as is shown in the figure, the volume is given, pressure also given. The mass of the piston has a pressure 350 kilopascal. So, or the mass of the piston create a pressure on the gas when it moves, create a pressure 350 kilopascal, which means that P2, as you can see here, P2, which is the maximum pressure in the process, is 350. P1 is 150. So we are providing heat to the cylinder, and we allow the air to expand. And when the air expands, as you know, we said that it's gonna push the cylinder upward, and this process requires work, of course. So we know that there is work done here by the air on the piston in order to push it upward. Okay, so now we will find out the requirement in this example from Kahoot. So we'll go to Kahoot. I need you all to join the Kahoot. I'll share with you the number very soon. Everyone? Okay. Can you please enter this? I need your name appeared on my screen. Okay, Peter, Abdulaziz, Chris, William. We should have 11 participants here. There's one missing. Yeah, Janshi. Okay, good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Perfect. All right.
So you're marking the attendance?
Yes.
Okay, I can't really see from my screen.
No, I'm gonna call it now.
All
You
right.
can see it now? Can you see
Yeah,
it now?
yeah.
Yeah. Okay, so Abdulaziz is there.
Yeah, I'm here, doctor.
Ali, Bakhtiar,
Yeah.
Bandar is not there. Okay, Chris there.
Yep.
Elias.
Yep.
Yes. Imran. Yes.
Yes.
Jingshi.
Yes.
Thank you. Kandakar. Kandakar Faisal. Kandakar. No. Okay. Asif. 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 Tariq.
Yes, sir.
Thank you. Mervin.
Yeah.
Muhammad. Muhammad. No. Okay. Neo.
Yes, sir.
Thank you. And Pendle?
Yep.
Pendle, yep. William?
Yes, sir.
Good, thank you. Yep, thank you. Okay, so go back to our competition. All right, so everyone there. Okay, so let's start. You know that the question I already explained to you the question. So each requirement takes 1 minute. So if you can prepare your calculator and scrap paper, so you can do your calculation on it, and then you can choose the right answer. It's a multiple. You choose the right answer from the screen. Okay. So let's start now. So we need to find T2, use the gas formula, ideal gas equation, which is All right, good. So we have 6 correct answers. Yeah, so as you can see, we applied the formula PV equal MRT. And because this is a general one, we can apply it for both points, so to P1 and P2. So we can say P1 V1 equal MRT and P2 V2 equal MRT. And because MR, both sides are equal, correct? We can reduce it to this. We can say P1 V1 over T1 is equal to P2 V2 over T2. So we have pressure, initial pressure is already given. We have the volume, initial volume given. Initial temperature is given from the figure, and also we have pressure 2, volume 2. The only thing we don't have is T2. So we can solve the equation for T2. Okay, so it's straightforward. Do you need explanation for this step?
All clear, sir. Thank you.
Yeah. Okay. Okay, so that's the first one. Okay, so we have Elias at the top. We'll see now. So again, work done by the ideal gas. The pressure is constant. Remember, W is equal to P delta V. So the change in the volume. So straightforward, you know the pressure, you need just to find delta V and multiply by pressure, you get the work. Why only 6 answers? Yeah. Yeah. Okay, good. We have 8 correct answers. Yeah, it's just direct substitution. Just substitute the values in this equation, work P delta V, and you'll get the answer. Okay. Okay, we have William at the top. Third question. The mass of the air if R is 0.28. So now we know the R, we need to know the mass of the air. So it's just simply PV equal MRT. Substitute the R value in this equation and find out what's the mass, because all other values are given. Direct substitution, just substitute the values and find what's the M. Remember, T must be in Kelvin. Yeah, correct. Yes, that's fine. Even if you made a mistake, as long as you know how to do it. Yeah, if you don't know how to do it, please let me know from now. Because this is the idea of this practice. We need to just allow you or give you a chance to do it yourself and find out if you have any difficulty. So this is quite important equation or formula, ideal gas equation. You need to know how to use it. Okay, so that's the mass of the air. Okay, good. We still have William at the top. Okay, this is the number 4. From table 821, find U. U1 and U2. You need to open table A21. Just go to this temperature and find out what's the sorry, this is quite short, should be 1 minute anyway. But you know what to do, right? Let me take you to that. So this is the table A21. Everyone can see it?
Yes, sir.
So if I make it bigger, we said the first temperature, the initial temperature was, sorry, the initial temperature is, what was the initial temperature? 300, correct? So if you go down to, on the first column here, this is for ideal gas, property of air, we have air. So if you go down to 300, temperature 300, which will be at this point here, at this temperature, you can find U value, which is this one, which is 214. And then point 2, the end of the process, was at temperature 1400. So we go to the table again, we go down, check where is the temperature 1400. We'll find it somewhere here, this one. At this temperature 1400, the U value is 1113, okay? So this is the way you find U value of the air. You go to table A21 and find, based on the temperature, you follow the temperature column and then find out the internal energy at that temperature. Is it clear for everyone? Please let me know from now. Any question? Okay. Right. So again, let's go back to this. Now, still have William at the top. Okay. The last question. Find Q if W was given. So W is given. So what's happening here is we have Q. So Q entering system minus W must equal to delta U. We're given U1 and U2, find out W. This is the energy balance. Correct. Yeah, it's quite simple. Just substitute the values for U2 and U1, and you have the mass. Of course, you didn't forget to put the mass. You need to put the mass here, multiplied by M. to find out the find out Qn, how much heat we added to the cylinder. Right? Any question before we finish this? Okay, let's see who's the winner. So number 3, Tariq. Abdulaziz, number 2, and William, number 1. Thank you, everyone. Thanks for your contribution in this exercise. Again, the idea of this exercise is to allow you to practice what we gave you in this lecture. And please, if you still find trouble or difficulty in any point, let me know, please, so I can explain it again. All right? Good. Thanks all for you, everyone. Okay, let's go back to our question. So you can find the solution of this in the material, in the lecture material in views. So please refer to this. And then also you'll find the complete solution for all the steps. Okay. All right, so we have another question here, another practice for you. Of course, I will go through this question, but need you also to interact with me, please. Again, as we said, because it's a closed system, we still use piston and cylinder. Okay, so this is a piston and cylinder device. And as you can see, we have initial condition. We have the mass already given in gram. So you need to change it to kilogram because all our values in kilogram. We have initial pressure and final pressure also, because they said here P1 is equal to P2. So because of this, we know both pressures. So pressure 1 is 300, pressure 2 also 300, and then what we call this process, if we have the constant pressure? Isobaric?
Yeah.
Correct, isobaric process, correct. Thank you. Okay, so the pressure maintained constant. As you can see, there is a heater, electric heater. This electric heater, as you can see, is a resistance. So from your, probably you have studied this before in physics or electricity. If you want to find the heat produced by a resistance, you can simply refer to the Ohm law, where you can say the voltage is equal to current multiplied by the power, W, is equal to V times I. This is voltage. Voltage multiplied by current. Okay, this is from physics. So this is to find out the P, power, they call it in electricity or in kilowatt. Okay, so in this case, we know that how much heat added to the cylinder if you know the current and the voltage, they're already given, both of them. So that's one thing, good. This voltage was provided in 5 minutes. So we can find out how much energy produced or added to the cylinder during 5 minutes. So at the same time, a heat loss of 3.7 kilojoule occurs. So as you can see from the lower part of the figure, there is heat loss Q out. And we provide heat, but in the meantime, we lose heat. So we need to add this in our equation, in our energy balance. Remember, in the energy balance, we said we have to add all the values in energy balance. Yeah. So in energy balance, we remember we said we should add all the values we have to Q in minus Q out, and then also plus W in minus W out. This must equal to the change in internal energy of the system. Yeah, correct. So we have to add all the amount Q in the system, whether it's in or out, and also all the work in the system, whether it's in or out. Of course, plus it should equal to the delta En. Okay, so go back again to the question. First requirement is for a closed system boundary work W. Show that for a closed system, the boundary work W and the change in internal energy in the first law relation can be combined into the one term, delta H, which is the change in enthalpy. So we need to show that the change in the work or the boundary work and the change in internal energy can be combined into delta H for constant pressure process. And then also we need to determine final temperature of the system. So we'll take it one by one. So in this one here, as we know that delta E is 0 because we don't have change in kinetic energy, potential energy, and also there is no change in internal energy of the system. So therefore, we can eliminate delta KE and delta PE. And we only say delta E is equal to delta U because this is where we change the internal energy of the gas, or sorry, of the saturated vapor, saturated water vapor. Okay. So again, now how to find this? We know that the equation we have should include Q because we have heat loss from the system. We should include also W because this is the work or the power of the resistance, electric resistance. And also we should include the change in internal energy of the steam because we are changing the temperature of the steam, then this must also change the internal energy of the steam. So we end up with this equation. And for the gas, for a constant pressure process, the boundary work, we know that now how to find the boundary work by applying this equation. W is the pressure multiplied by change in volume. So we know that change in volume represents the boundary work of the gas. Okay, and the other one is, this one is the power provided by the electric heater or electric resistance. Okay, so if we know all these values, then we can simply solve this equation. So we already given these values actually, but now for the first requirement, if we simplify this equation, we say Q minus W, we take this part to the other, take this term to the other side of the equation, and then we can simplify this side because U plus V is H. So for each one of these, we can give it H2, and this one is H1. All right. So we can reduce the equation from what we had before to this one. Q minus W is equal to change in enthalpy of the point 1 and point 2, or change in enthalpy of the steam. Okay, and then we can go to steam tables and find this easily from steam tables. All right, so let's go back to the second requirement. So now W, which represents the power of the electric heater, as we said, it is based on Ohm's law. We can multiply the voltage by the current, multiply by number of seconds, because this is where they said we have 5 minutes, the heater open for 5 minutes. So we can multiply this based on this requirement here. You can see here, they said it's 5 minutes. So we are multiplying this by 300 seconds, sorry. We could change 5 minutes to seconds, multiply by 60. So we get 300 seconds. We can find how much work added by the heater or by the electric heater. We can call it work or we can call it heat, doesn't matter. Because we have heat loss and we have heat gain. We can call it heat added by the electric heater, or we can say work added by electric heater. It will be the same because the equation will not change. And then to find other values of H, remember we said we need to find H. So we can easily find H for 0.1 because we know the pressure of 0.1 and we know it's saturated steam, which means that it's falling right at the boundary of saturation line. Can you see here? Sorry, this is 0.1, and 0.1 actually H1 is equal to Hg from tables, H gas. So if I go to steam tables, saturated steam at pressure 300, I can find Hg, which is H1. Okay? Is it clear for everyone? Okay. Right, so we go back to the last part. So now I can find H1 from tables, table A5, and find H1 is equal to 2725 kilojoule per kilogram. Now, the other thing is you need to find H2. So actually H2, we all need to do is substitute in the equation. So this is our equation. We end up with the last equation. We said that work in, which is the electric heater work or heat, minus the Q out, which is the Q lost from the cylinder to the surroundings, equal delta H, which is M multiplied by H2 minus H1. So we know H1, we know mass, okay, we know the Q, and we know the W. The only unknown is H2. So H2, we solve the equation for H2, and then we find that H2 is equal to 2,865. All right, is it clear? I know it's have some difficulty in understanding this now, but I believe if you go after the class and try to revise this, watch the video again, you'll be fine. I'm pretty sure. You need to do it yourself because I'm talking now. You need to go to I'm telling you now, you need to go to the tables, and it's quite hard to understand this without going yourself to the tables and find out the values. So please try to practice this yourself after the class, and it should be fine. Remember, the quiz for tomorrow requires tables, so please try to practice yourself. You know how to use the tables, especially the saturated steam tables.
Okay. The two table A4 and A5, is it?
Yes, yes.
So how many questions will be there?
It's only one question, like you know the Kahoot one. It's same
Yeah.
question but has different requirement. So let's say one question with 10 requirements. So each very simple requirement. But all you need to do is you need to know how to use the tables, and also you need to know some of the equations given in the last 3 weeks.
Doctor,
Yes.
can you print off the formula sheet?
It's in the, I'll show you, it's in the in views, I'll show you now.
In the quiz, during the quiz?
Yeah. I told you, you can, it's open book, so you can download the formula sheet, but it don't have many formulas so far. I mean, it's still up to week 3. It's like limited formulas, but it's up to you. You can download it.
Okay.
So the quiz will be multiple choice, is it?
It's multiple choice, yeah.
Okay, so we do not need to upload any papers.
No. Quiz 3, you will upload a paper.
Okay,
Quiz
so
1 and 2,
yeah, okay.
yeah, because we need to prepare you for the final exam. So quiz 3, you will write on a paper and then upload a paper to views.
Okay. So at the end of the quiz, we don't have any submission link.
No, you don't need to submit anything. It will once the time finished, then that's it. It will be auto marking. Okay. So that's all. Now it's 23. Let me see if you have still time. Yeah, I can show you here, like if you can see here, this is, can you write down this? We have pressure 300. So we have P is equal to 300. And we have H2 is equal to 2865. This is in kilojoule per kilogram. Okay, so if I take this to the table, I want to find what's the T2. Remember, we are working in steam, superheated steam region, correct? Because if I take you back to the drawing, can you see this drawing? So number 2, stage 2 is far away from the saturation line, from this line. So if it's away from the line, it means we are in superheated region. So superheated region, which means that we need to use different tables. For this region, we have table 4 and 5 in this region. In this region, we should use table, which one? 6, yep, for superheated. Okay, so remember now, we have pressure 300 and H 2865. So let's put it on the paper. 2865, and pressure is 300 kilopascal. So now if I go to the tables, let me go back here. This is the table I have, right? And this is table A6. I want to find what the temperature at pressure 300 kilopascal and H 2806. So what should I do? First of all, I need to choose the pressure. So if I say 300 kilopascal, if you can see here, the pressure given in megapascal. So 300 kilopascal divided by 1,000 will be 0.3, correct? Megapascal. So 0.3 megapascal, then I should work in this table. This is my table. Now, if I know the enthalpy value, which is this one here, sorry.
2865.
Let me go take it back again. So if I know the enthalpy value, which is 2865, so follow this column.
Third column.
The third one. So for this 286, what's the temperature?
200.
200. So I can get the temperature from a table based on the pressure I have and the enthalpy I found from the equations. Okay, so this is the way you found the temperature if you know the pressure and enthalpy of superheated steam. Is it clear for everyone? But you need to know that this is superheated steam. Okay, you can't apply it for saturated steam because it's different thing. Only for superheated steam you can do this. Okay. Any question? Right. So the last thing we need to mention here, specific heat. Probably the time would not be enough for us, but I'll just give you a quick information about specific heat, and next week we'll give you another example about how to find properties from specific heats. Specific heats is the energy required to raise the temperature of a unit mass of a substance by 1 degree. So if you can raise the temperature 1 degree, this is the amount of heat required to raise the temperature, one temperature of a certain substance. And for each, of course, for each substance has its own specific heat. So we have two types of specific heats. At constant volume, we give it CV, we call it CV because it's C for specific heat and V for constant volume. And also we have specific heat at constant pressure, C, P for pressure, okay? And there is a relation between CV and internal energy and CP and enthalpy. So to find, for example, to find U, you can simply say U is equal to CV times T. And to find H, for, of course, for ideal gas, you can say also CP times T. Okay, so this is for both sorry, yeah. Okay, so we can say U is equal to CVT and H is equal to CPT. Okay, so if you can't find the H value from tables or U value from tables, you can apply this equation. If you know CV, of course, or CP. And CV and CP, like R value, it's given in tables also for each gas. I will show you now very soon. So if I take you to the next, but just a relation between CP and CP is the ratio between them called K. So K is the ratio between CP and CV. And this is given in this here. So CP divided by K is equal to CP by CV. Okay. All right. So we'll talk about this in next week because already time is over. I don't know if you have other classes now. Do you mind if I keep doing, let's say, this for another 5-10 minutes? Anyone want to leave or?
No, I have no classes. I don't mind for me.
Other students?
Me too.
William.
I don't have any class.
Sorry?
I don't have any class, sir.
Okay, so what about William, Peter, Nay, Mervin, Meleh, Jengshi, Imran, Ilyas?
For how longer? Much longer?
10 minutes.
Yeah, that's good.
That's good. Okay.
Fine, sir. Yeah.
Okay. Thank you. All right. So let me go quickly. So now we know that the ratio between CP and CV always, we call it K. So K is CP by CV. And always CP is greater than CV. As we said, these values given in tables. So now, for example, for helium gas, the value of CP and CV, if you can see, is given in this in these two figures. I know how much internal energy for each one of these, because if I know CV, I can find internal energy for this condition. And also, if it's, let's say, if I have CP, I can find also H for this state. For air, if you can see here, air, between this temperature, this is the amount of specific heat for air, and this is CV for air at 300 K, and for 1000 it will be changed, because when you change the temperature, we'll see CV or CP will change, but we'll all these given in tables. I'll show you very soon. Okay. So let's say this is the table A2. As you can see, table A2, it has R value, as you can see, also have CP value, have CV value, and has K value. So all of them given in tables. So in the question, if you don't find any of these values, you can always refer to this table. Refer to this table A2, and you can find the constants for each gas. Okay. And also there is other table, this one, ideal gas specific heat for different gases. As we said before, with the temperature, the specific heat will change. So for example, if you have a question with air, you come to this table. This one is for air, as you can see. This one is for CO2. This one is for carbon monoxide, CO, and so on. So you take the table that for your gas. So let's say if we are working for air, you take the first table and see what's your temperature. Find the temperature that you are working on. And then at the certain temperature, you can find all the values for CP, CV, and K if you want a K. Okay, but depends on what temperature you are referring to. So once you know the temperature, you come to the table A2 and find CP value. So now if you know CP value, it's easy to find H, enthalpy or internal energy. Okay, so there are other way of finding U and H, but as I said before, we'll talk about this in next week, because it's really still have some more to talk about. But I want to compress it here all in this class. So let's work on this next week and show you how to find out enthalpy and internal energy from specific heats, CP and CV. Okay. Any question before we leave?
Thank you, sir.
Okay, guys. Okay, so yeah, just try to revise the tables, please, and the last 3 weeks formulas or topics, and you'll be fine. It's a quite simple quiz. It's 10 questions, like 10 requirements for each. It's same question, but it has 10 requirements. Each requirement is very simple, but it's multiple choice, so you need to work it out. And also remember, it's random questions. So don't rely on your colleague or your friend. You call him and tell him like, what's the answer of this question? It will be random. So don't put yourself in this. Otherwise you're gonna get 0 because everything will be different from your friend questions. Okay, so please make sure that you do it yourself And as I said, it's simple. It's not hard.
So the
Okay.
quiz will be on the views, right?
The quiz will be on views.
On the
Yeah,
view.
we'll. Yeah. So your teacher Ahmed will show you how to access it. Okay, when he meets you tomorrow, we'll show you how to access this. Yeah. There's a question here, Elias, or this is too late. I forgot to answer V. Or sorry. Is it like Elias? Do you have a question before we leave? You sent a couple of messages on chat box. Sorry, I didn't see it. Elias? No? Okay. All right. So make sure that tomorrow, please keep your camera on. Okay, because for every quiz, we should keep the camera on. All right, any question before we leave?
No, sir.
Okay. Okay. Thank you, everyone.
Thanks.
See you next week.